Good morning, and it's afternoon. Hopefully, I have WSL. Let me do it in Kali. Hi, hi, hi. I'll do some binary exploitation, all the challenges in Pico, and learn some things about binary exploitation. That is what I'm planning to do. This stream is going to be very long. It might run for like 4 5 hours also. I don't know. My goal is to learn the binary exploitation and then in buffer overflows and heap overflows. I just had a create a goal. Can I create? These goals are different. So let's go. Go. This. Let's complete everything. The adjustments are done. Fine. That makes sense. Close this thing. Perfect. Let me also open. Ah, so start with Pico CTF. Do as many problems as I can, and then I'll switch. Login. Perfect. Yeah. Okay, fine. Sir, so we have problems here. Let's only focus on binary exploitation because that is what I want to do for today. Just easier, all are done, I guess. Medium, some other, so let's. This one, heap jit, I think this is pretty easy. You know, uh, the overflow style. Sorry for the housekeeping part. I have to do this. Let me get the source and binary. I think I already solved this, but anyway, I'll do it again. Okay, makes sense. I think I don't have code, VS Code or something, I guess. Let me install that. This is going to be a long thing. His marathon, I guess. Damn it. Hmm. Oh, so the problem here are the overflows just stack concern. Download the binary, download. So additional details will be this is based on heap overflows. You can see that by the name itself. Pretty basic there. I mean pretty straightforward there at least. Uh so heap overflows. I'm very new to this heap overflows. So one of my main goal is to learn the heap overflows properly after at least by the end of this uh, marathon at least. Uh, heap smashing is a type of buffer overflow that occurs in the heap data. So heap is actually assigned when you use some memory allocator tools like malloc, pointers, and calloc free. So all these things will be within the malloc. So I mean, in the heap area. So for example, what's called free? It'll buffer. So it'll create a space for you. So consequences result in the data corruption and unexpected behavior on any process that access the memory area. On operating systems without memory or protection, they could be any process. But the problem with heap is you'll not find this instruction pointer and all those registers there. So I don't know. Kind of curious how I could do the code execution on heap through heap overflows. Like that's something that I want to learn. Prevention and detection, unexpected, like make your stack unexecutable, randomize the addresses, introduce anti-checks to the heap manager. Yeah, makes sense. Makes sense. I mean the basic British basic straightforward things. So this one. So we have a couple of pointers here and you can see a malloc function going on there. So let's see what's actually the vulnerability. Let's start with main function. So there is an init function being loaded. So init function tells you welcome to the heap, put the data so that the tampering cannot be done, and then the malloc flush the this is just flushing the output, so all the output will be gone. Uh, Malloc is the input size, which is a static something like 5. Okay, makes sense. Where else? Where are we? Yep, init right. Okay. So and then string str and cpy. Okay, makes sense. It is copying input data. I mean the size of input data from because this is being transferred to this. So str and cpy again. So that makes sense. And this function doesn't look any vulnerable, at least because it is using some standard functions like str and cpy and all. So could be good. What else? Print heap. Print heap is then just printing the heap. Makes sense. Hmm. Choice. Okay. For printing the choices. Do you have anywhere gets or something? Write buffer. Let's check the write buffer function which I missed. Looks like a kind of standard strong function because they're using all strong functions like fgets. Scanf. Let's run and see what happens. But before that, I want to install GEF. This is just like beautification for your GDB, at least that's what it means. Uh, oh, of course, GDB is there now. I think I should also install 32-bit thing, 32-bit architecture, because most of these binaries will be in 32-bit. 32-bit Linux for running. Yep, I can follow some basic things, and yep, I can do that. I think I used to follow this guide very long. This just acts. Okay, leaving default. Nothing crazy. Watching. Fine. 12 shift D. I think this is chmod plus x file chal. This is a 64-bit. Okay, we don't need something like crazy. So it is asking for me to print the heap. Okay, let's write into the buffer. Let's input like as much content as I can. Okay, what else? Win. That's it. What is the funk? The goal? I'm doing binary exploitation. Let's just stack concern. What's the hint here? What part of the heap do you have control over, and how is it linked with the safe bar? Okay, maybe we should look it in the GDB structure and all. With that, let me get the GEF installed. person. Write to buffer again, which will be like so many A's. And now print the safe value. Okay. Print the flag. What is print the flag doing? String compare is vulnerable to the buffer. Now it makes sense. So it's all in the check-win function. I mean, which is running in the flag function. Hmm. This will secure. We should rewrite the safe variable. That's what it is. Let's see where the safe variable is. Hmm. Safe var is exactly down after this input data. So whatever, if we keep it more right. So what's happening is like I understood what's happening. So input data has pico and safe var has pico. If you observe it clearly, and the check-win function is checking if it is not equal to pico. So if the tampering is done, then pico won't be there right in the safe var. Then you will win the flag. For example, let's see. Let's run this again. If I run this again, if I write into the buffer with phi, for example, and if I print the flag, now you see it looks like nothing is there because Biko is still there. And if I still print the heap, you can see Biko is still there here. So my goal is like this is the input data, this is the address of input data, and this is the address of safe var. So if I inject more data and corrupt the next heap, so that should be it. So I'll try to let me see a whiteboard. I can use my tab and make some things. Whiteboard online free, for example. Let me get this thing. Start with the whiteboard. 24 hours is so much. Okay, still loading. Don't want to. I just want to share the board. Copy link. Okay, I'll send mail to myself. Minute. It would be better if I can write down everything so that. Just a second. Let me get my tab. A charge. Little bit. Okay, perfect. I think I joined. Yep. So So I think in my past, so I'll give a quick brief on what stack and queue is. So stack and heap is. So go back to the example, and okay, no, let me give you a simple brief. So whenever a function is created, so there is going to be a stack. So stack is nothing but imagine a stack like uh, a rack of CDs. Like you put everything in the CDs, and only thing you can remove is the last one. The last in first out. So whichever comes last will go out first. So that's what a stack is. So whenever a function is declared, so there are two pointers called base pointer and stack pointer. These are called EBP or RBP or ESP or RSP. So R is specified when you are dealing with a 32-bit architecture. R is specified when you're dealing with 64-bit architecture. So that's the basic difference. So whenever you let me erase this. Whenever a function is created or called, so this is what happens in the underground. So it just creates some kind of a pointer. So for example, EBP and ESP. So it depends upon the buffer size. The ESP will be moved downwards. So now this is ESP. Okay, this is the buffer size. It depends on what variables you are loading and stuff like that. Okay, so this is nothing but a small stack. Okay, these are pointers, like the pointers, like it points where it is actually locating to and stuff like that. So this is what it is. And the stack always grows downwards. Okay, but for example, there is a name. For example, name is a variable that you are reading. Okay, so five is the only name of size 5 is the only variable you have at the moment. So your buffer size will be obviously 5. So whenever you're including, for example, if you're including like so many a's in the name, for example, and assume that there is a gets function being used, because buffer overflow only works when you're dealing with some vulnerable functions. So it won't work every time. So if you use fgets, it will not be a possible. It's not going to be possible. So assume that there is a function like this which causes a buffer overflow, and whenever you include some content like this, maybe like 100 s, what happens is, like as I told you, the stack grows downwards, but the content goes upwards, and the whatever you fill, it goes upward. Okay, and there is one more instruction. There is one more register called as EIP or instruction pointer. So this particular register holds the address of next instruction to be executed. Simple. So whenever it just holds like what should I run first. It's like a guide kind of checks like who manages a queue or list, saying that okay, next you are going to be the one, so something like that. So if you are able to rewrite this EIP, then you could actually bypass this whole execution flow. Okay, so this is what a stack overflow in general means. But the problem is, the in the heap overflow, for example, if you use malloc, calloc, these are for memory allocations, and free. Free is to remove the space. Malloc and calloc are used to give a certain space. Like maybe like you say like I want this much size for my operation. Then you can use malloc. Malloc and calloc, the main difference is in the calloc you can actually specify a default value. Okay, like for example, if you want a malloc size of 10, it is just going to be a 10 address space, like this, from this address space to this address. This is what malloc does. But calloc, if you ask 10 and give 0, it will fill, like I'll give you example. So this could be a 10 byte block for malloc. But for calloc, even this is 10 bytes, but you have like all zeros of 10 zeros, for example. That's what I'm trying to tell. Uh, let me. Okay, cool. Okay, whatever. So whenever you use a functions like malloc and calloc, there is going to be a separate area called heap. A heap is assigned. A heap has a different structure of what stack does. So I'm good. I mean, I can understand and I can tell talk more about the stack overflows, which is this, I mean the buffer overflow. But heap overflow, I'm kind of not too familiar. And coming to our example, we have two variables here, which is input data, sorry, and this is safeware. Okay, initially input data is something that is allowed. Okay, like you can write here. Okay, but for the safeware, if it is already defined, it's like a hard coded value saying that because is the value which is used for the uh, in the safeware variable. So our goal is like if you are able to corrupt this safeware, you will be getting a shell. So the problem here is it's not string compare in my opinion. String compare is not the vulnerable function. I'm really sorry about that. Shouldn't have said that. The problem is within the heap itself. So we are just in. So here we are just inputting Pico for the first time, and when you're writing it to the buffer, you're writing it without any memory checks. I mean bound checks. Like there is no bound. Like you're not specifying specifically that okay, you can only write 10 or you can only write 5. I think what's the malloc size? I think it's 5. So that is something it is missing. So since you are missing, right, you are actually messing up. For example, if I'm giving so many A's, I go back to my example whiteboard. If I give so many A's, I'm actually corrupting safeware as well, converting this to, for example, some so many A's. So this is what I basically understood uh, from a high level overview. But I want to learn more too, and that's how the problem is solved. If you send multiple, you just need to overwrite this thing. That's all. Yep, you just need to overwrite the save pair within the heap location, and that should be good enough. So the problem here is like I don't know much about heap overflow, so that's one of the reason why I want to do this here. I mean, learn by the end of the stream. But yes, uh, let me clean everything so that we can use it for the other time. Yep. So I think that should be it. I mean, that's the basic underlying concept here, but I want to ask ChatGPT and AI to see if my understanding is correct or not, so that I can move forward with the next challenge. Okay. So want to get some high level clarity on things even before what moving to the next topic or concept. So I'm just clearing this out. Yep, perfect. So let's copy the code. Let me copy this code and let me ask ChatGPT once. Let's see what it says. Hi. So how do you overwrite? It's that's something mm, it is like if you input more data than the size of input data, which is going to be the size 5, it is actually overwriting the next location within the heap, which is safe where. But the problem is even I'm not sure clearly about is there are no vulnerable functions. Like this is the reading through secure functions only. But where is the issue is the question, and I'm asking ChatGPT. I mean, I was able to solve this problem, but no, I'm not satisfied with my answers. I'm just looking for proper answer. even though it shows a heap of due to the scanner. Okay. So yeah, that's one thing I understood. Like the size, the reading, right? What the input data, whatever you're giving it to the input data is not being monitored clearly. Like that, it's not being checked exclusively that it is only 5 bytes or something like that. It's just taking whatever it wants. So what ChatGPT is saying is scanf doesn't limit the input size, which makes sense. So just reading whatever it can, since the input data is allocated to 5 and in any input longer than 4 characters will overflow into the adjacent heap. Okay, I mean that's how heap works, I guess. I mean if you overflow more content, I think it should be gone. But anyways, if you have a proper check for the length, the bounds, if you set a proper bounds, then I think it shouldn't be an issue. So but yeah, let's see. Heap overflow, the program allocates two heap chunks, input data and save where. That's what we did. Because heap allocations are usually placed adjacently to each other, overflowing input data can override the save where. That's what we actually did in our attack, which is very simple though. If a user inputs a string longer than 4 minutes, okay, cool. That's what we did. So the problem, the fix they're suggesting is if you use a scanf with there is this percentage. I can copy this and I can paste it here. For example, if you use something like scanf like this, right? Uh, which is only looking for 4 characters to read. So that would be really good thing. The reason only 4 characters is like the last character in the string is going to be a null byte, so that it tells you when to terminate your string. So this makes sense. So memory bounds, that's the issue. Or you can use fgets with the size. You can specify the size, so that should be good enough too. So this is a basic problem. That's fine. Yep, yep. So let's keep this whiteboard running. I might be using it for several times. So that's the heap overflow problem. We'll just get the flag, very simple. Let's do heap one. Let's try heap one. Create a directory. I don't know. I mean, I literally don't have much idea about this, but let's try. Still, I'll try and you know, let me learn something. Hmm. Okay, let's focus more on heap overflow. So, and I'll be using ChatGPT and all in the meantime, so that I can get a good understanding on what's going on. So, can you control overflow? Let's copy link. Heap one. Source, the source, right? I think we copied finally. Yep, perfect. Let's see this code first again. So we have a flag size, some basic allocations here. And again, I think we are uh, checking the safe where again. So if we rewrite the safe where, I think that should be a win for us, I guess. Okay, let's see how they implemented. There is a print menu, which is basically printing. And we have uh, same implementation of malloc here, input data and str safe where. So that's nice. And again, there is no interesting. What is being checked here? I mean, I don't find much difference. Scanf is pretty much remains the same and it reads more content than it can. So okay, the safe where should be Pico now. No. So what's safe where containing right now? It's Pico. not of this will return true, right? True of not is false. So this should be false. Wait, let me ask. Let's see what this means. What does strcmp return? Return 0 if the strings are identical, not of 1 equal to 1. So we need to rewrite safeware in such a way it should be equal to pico. Makes sense. Return 0 if the strings are identical, it returns negative if the first string is lexicographically small. Yep, so yeah, that makes sense. So we need to rewrite safeware to the to the value which says pico. Makes sense. So pico should be rewritten to pico. Yep, this is pretty straightforward. I mean, same as the previous challenge, but instead of overflowing the content as much as you can, we are only overflowing to a certain limit, and you are actually rewriting safeware to the pico. I mean, I think if you change the first character from P to B, I think that should be sufficient. Let's try. bdb dot slash. Oh, this is sorry. I should make it executable. So run first. I think it's the same five, right? So okay, let me try this once. I don't know if it should work or not. Uh, okay, we have Pico in the first one is what do you call it? The input. Second one is the safeware. So write to the buffer, which is going to be 1, 2, 3, 4, 5, and then P, for example. So now let's print the heap. Okay, and write some more. Right. 2, 3, 6, 7, 8. Okay, let me run this again. As I messed up, I guess. So before that, create a pattern create 10, for example. Okay, 10 is too small. 12, 20. Oh, it looks very pretty similar. Let's see how it goes. And let's run. Let me write to the heap first. Now if I print the heap, no. So I think the sizes, I think I messed up with the size. The ratio, it is 5 size 5. Let me do exit. Let me create a pattern of 100 maybe. Let's see. Copy, run. Uh, the buffer, print the heap. Okay. Now you know where it is actually rewriting. So let me open a new tab. So this is the one which we actually wrote, and this is what it is there in. So I think till here, from here onwards, I think it is rewriting. You observe carefully, right? So They started writing from EAA, control F, E. There's only one. So if we can pass till here, we put it P. Let's see how it goes. Anyways, I think the P passing P should directly shouldn't work, but I just want to try it once. Uh, right. Okay. Now it makes sense if I put Pico. See, see again. So I hope you are getting what I'm trying to do. Right to buffer. Now if I print the buffer, it is Pico. Now if I print the flag, it should print the flag. It should print the flag because. Okay, let's do it on the server itself. Let's see if it works actually. So I'll give you a good explanation once I know that the challenge is actually working. I think it is. It looks like it is working, but no, it's not. Okay, here it is. So, uh, right to buffer. This is the content. Let's print the buffer. Okay, and flag. Yep, we got the flag. I'll tell you what I did. It's very simple in my opinion. I'll tell you. I'll give you a quick. I'll draw and tell you. Yeah, this looks kind of simple. I mean, I just did the data corruption again. It's not like what I have in my mind is I want to do something on a heap overflow such that I could actually get a remote command execution or something. But at the moment, I'm only created with this data corruption thing. So back to the drawing board. Let me tell you what happens here. So again, okay. Again, we have like two. Oh, okay, perfect. So again, we have two variables called input data and safeware. So these two are again using malloc and get their space assigned, to be honest. And once they do that, they all have a size of like 5 limitation or something. So now this time there is a heap allocated. For example, half. This is for input data and this is for safeware. So input data again is not looking for any kind of checks. There is no checks being going on. So it just reads whatever it can. But the function here is checking if safeware equal to pico. I mean in the Python terms to keep it simple for you. And return flag. But initially when the moment they assigned it, they actually included a pico within this safeware. So pico is already there here. So our goal is like to rewrite this safeware from pico to pico so that you can get the flag. So I carefully injected some content here, like some A's here, and made sure to rewrite this pico to pico. That's what I actually did. So if you see my payload, it's like this is nothing but I don't know how many characters it is. I just went by the brute. I went with the brute approach. I'll be honest, and yeah, and then pico is something that I used, and then I corrupted the safeware so that we have the flag. That should make sense. I hope it's clear. Yeah, so this is how it should be going. So we are just corrupting the data again, so that's the goal here. So Yeah, let's do the heap too. Let's see. Let's go. Let's go. Let's see. Can you handle function pointers? I am not sure. I need to learn this thing. So yes, sir. Let's do this. I think function pointers. Okay, let's see. I hope it's clear. I mean, even I'm doing this heap challenges now. The first one, I think I did it by just brute approach. Like I just injected as much content as I can, and I just did, I guess. But, yep, let's go to the heap two. And this iPad is looking good for me, even at least for me to learn. Project W, Control L, dot. Yes, yes. I think I can leave it like this. It's not a big deal. So if you want how I'm writing, this is how this heap structure works. So heap is there in such a way that the memory allocation. So let's go and see. Allocates memory block of the size you specify. That's it. You're just asking like give me this much memory. I don't want. I mean, you're just asking in advance like I want this much of memory. So that should make sense. So, since the both blocks are in the same heap area, so if the proper checks are not done, you can rewrite the other block. It's like same buffer overflow where you're writing. There you're writing instruction pointers. Here you're writing a memory space itself. That's what we're doing. I think that's an easy way to put it out. Okay, let's do. mm, Okay, copy. Perfect, perfect. So now we have one more thing. We have pointers here. So let's do a quick refresh. Let's go with gigs for gigs. Okay, or else let's use Reddit. Sometimes Reddit explanation will be very good. Bro, the internet is literally unusable without ad blocker, man. Don't want to see something sus, at least on this chat or during the stream. Oh, best pointers explanation. So pointers, like, I'll give you a quick brief instead of directly going to what people are saying. Let's go back to our again. Erasing takes a lot of time for some. No worries. Okay, perfect, perfect. Okay, so now, so what we can do in general is like, for example, if we specify int a equals to 5, we are we're just giving your compiler or whatever it is, your language to tell, okay, store value 5 in a. So a is nothing but it is going to be an reference, like for example ox 1 2 3 4 5 6, for example. Okay, so even a is holding that. So this is a general way how you declare a values and all. But with the pointer, you can specify the address of the location actually. So to keep it simple, like for example, here the pointer, so pointers are actually mentioned through star. So star b, which is nothing but a pointer b which stores a data type of int. It cannot store, if you have like 5.5, for example, one more floating value, that cannot be stored in b. It can only store the addresses of the values which are of integer type. So ampersand a here in C at least tries to tell you that it is the address of actual A. So now the B is actually holding the address of A. So it is nothing but you can you can reference that and get the value of A again. So which is going to be 5. This is something that I know. I mean, this is a basic thing. So your goal is like you can store the addresses. Okay, this is weird. I don't know why I opened this. Let's not recroll or something sus. Okay, so this guy is referring to int, and this guy is referring to this, and this guy instar is referring to instar, and instar is referring to int. I mean, it's like chaining. Void star is pointing out to a space which is nothing, void. Interesting. It's nice. This is pretty cool, pretty cool. So it's pretty cool. So instar star is nothing but like referring to instar, and then star, bro. And I think you don't have to go too deep, at least for the buffer and exploitation. All the variables located somewhere in the memory. For example, in the image above, okay, what's this image? Variable a at address 2 and b at 1008. See this? Okay, a is at like 1002 and b is like 1008. Okay, so the content of a is 1008, the address of b, but when difference and bro, confusing. I mean, let's go out of thing. Let's use geeks for geeks. Point is a variable that shows the memory address of another variable. Simple, that's what I'm trying to do it in that. Instead of holding a direct value, it holds the address where the value is stored. So, you can, the good point with the advantage with pointers is like you don't have to create so many variables. Like for example, if you're calling a function, like you can use the same address, you can pass the address of that variable which you want to manipulate on, and you can use the same thing. Like it could be really cool. Like the address is going to be common throughout your program, and that address could hold a lot of information. So I think this is the example that I actually shown you. You can print and see. You can see the cool things, like you can see value of m is 100, memory address of m is, because we are assigning it to the address of m, I mean the pointer here, and then the memory address, something like this. Cool, cool. Percent p is the like percent d is to specify integers, percent p is to specify the pointers, so that should make sense. Point declaration. So to declare, we need to use before that. Okay, you can store a string as pointer too. The string is nothing but a character with a array of characters. That's all. And you can do something like this is something I have done, like in my things, like you can print that and it should print the gigs for gigs. It will be also easy to navigate. Like if you do s+1, which is going to be g like you can iterate through the whole. Sorry, you can iterate through the whole string as well. That should be cool. Array pointers and things. So now let's come back to the problem. I think that should be good. So we have a couple of pointers, x and input data. Input data right now is a pointer. And again, I think the input data again is a I think now it is a pointer and x is also a pointer. Okay, check win is kind of tricky. I don't know what this is actually doing. This looks kind of void. Oh, this looks kind of too. Yep. You know what to do? Let's ask ChatGPT. You can ask ChatGPT or you can simply search what this is. So it looks like our goal here is to run this win function. So now we are actually in the point of doing hijack. Now we are doing the actual hijacking, which we do in commonly in binary buffer overflows. Uh, so x is originally a character pointer. Okay, that makes sense. Int star x. We're casting x to an integer pointer. So this is what this is doing, it seems. So int star of x is casting from a character to an integer pointer. Okay, makes sense. I mean, that's how the C works. So yeah. So in text treats x as a pointer to the integer. Int star means it interprets the memory at x as a 4-byte integer. This is important because pointer functions are typically stored as 4-byte address. Okay. And then again, the star of is like dereferencing this x. So you're getting the address. This is expected to be a memory address of the function. Okay. And we are passing that address, casting integer to a function pointer. Our goal is to overflow x. That's the main thing. But I'm still trying to understand this particular thing. First, it's trying to type. Okay, let me copy this thing. Okay, let's go step by step. Let's see if I can uncover anything cool. Okay, so let's remove this. This is function, that like it means to be a function. Let me run and see the function. So confusing, to be honest. Okay, we know that it's going to be the case. Is it like we just rewrite the x since it is already a pointer? We are pointing this. Okay, we're pointing the x to some bin function so that it gets loaded. Kind of interesting challenge. Like, let's see the heaps of Pico and Bico. Right. Should create a pattern. That should be a better idea. That should load with the CD. Okay. I don't know how to do this, but I'm trying to understand what's going underneath. X, which is still Pico. Now it is AACAA. So we should exactly write till here. Control copy. Let's try. I mean, I'm just trying to do this. Let's see. Let's do this again. Print right into the buffer. I index. Yes, see. I think now it makes sense. Since the x is already a pointer, I think I should pass the address of the bin function so that maybe I could get the flag. The segmentation fault is because of x having some corrupt data or something. So yeah, so I think I got what to do at least now. Is it like straightforward? Can I pass the uh, address directly, or should I do some kind of font tools? We're doing the right Indianness. Okay, I should do the Indianness too. That makes sense. So first, let's do. There's no checksec. Okay, I'll tell you what checksec is. Checksec is a really cool tool. It gives you all the binary information. I'm trying to do a heap overflow. Simple. I mean, not simple. It's very complex. Not at all simple. I don't know why I call it simple, but it's very complex. So no executable is enable, no stack, nothing. So no ASLR as well. So yep, that's cool. So we have a situation here where we have to rewrite the pointer of x to the address of win function so that the win function gets loaded. I'm kind of confused on why this is doing that. Why is writing to x makes the function tuple. It's not like EIP, right? So the right question like EIP in x86 architecture, which directly controls the flow execution. X here is just a heap allocated variable. So why does writing X allows us function pointers? Stores the address, okay. The form storing the address. Okay, that makes sense. It will fail because when you're trying to print the flag, because uh, it X is not actually having any kind of an address there, so that will be an issue. So X should be rewritten with the address of win function. So how to do that? Let's go info functions. Can see. Okay, we have here. Okay, it's very simple to do. Object dump shall. I forgot syntax. Damn. These get some sorry. Yep. We can get the address of checkmin. So our payload is going to be one, which is going to be. Are there any little online little Indian tools, or we can use spawn tools? Python 3 on. Okay. Don't tell me that, and yeah, it's good, it's fine. At least it's going fine. I will do a whiteboard example of what's going on, so that please wait. Let me do this first. I'm expecting this should work at least. Okay, we have the address. Pass it directly and see if it goes. It doesn't go, it will not go anyway. So let's try this once. Print buffer, write to buffer, print x. Okay, print the flag. Okay. Should I make it executable? I mean, not executable. Just a minute. Okay, perfect. Do I have to write it in a separate format or see one more time? Okay, I know what to do. Right. Let's see function here code. See we let's use it into the byte format. I'm just writing it to in proper format so that it shouldn't cause any issue. Is it pass will passing directly will work? Okay, here it is not. I think sys.stdio.buffer. Do you think I should write first? \n. We'll try to figure out how to make this work. I can do it manually though. And should I also pass 4? I think this should be doing good, I guess. So what I'm doing is like first I'm sending 2 and then an enter, which is where I'm entering all this content, and then I'm entering 4 to see the flag. I mean, let me try on this first. This looks like should be done. I mean, I can write a Python script for that, but it is too much uh, overkill in my opinion. So let's see. Let's see if this can be done easily. Okay, let me do it once. Not working. Interesting. What if I do this manually? I mean, I know that it should be sent in the byte format, but heap, write to buffer, print flag. It's not working. No. Okay. Do you think I'm messing up with this code itself? I'm actually looking at a walkthrough. So can I? Okay, so it's almost same payload, but he used echo. But shouldn't we write it in the byte format? Let me try. Oh, it's not working. No, it's not. Can I print? Time. Is the function that I took is right? Should be correct. C011 and then all zeros. C011 and then all zeros. Yeah, perfect. Wrong. Okay, let me write some Pontoon script. Code exploit.py. Let's get all the content. Perfect. Host and the port. Of two. First we'll be sending two, right? Yeah, first we'll be sending right to buffer, and then p dot send line of whatever the thing we are trying to send. Okay, perfect. Okay, let's see. Let's run this manually and see. First, we are writing it to the buffer, and for example, all the content, and then we have to receive. How much we have to receive? We can have receive until p dot cv until, what is this called? Choice. Choice. Okay, should be good. Now we can print text. I mean, we can print flag directly. I mean, let's print the line of 3, which is or 4 directly. Receive line. Let's see. On dot remote, I guess. Okay. From pawn import stuff. Oh, pipe format. Should be. Let me print this receive lines multiple. I don't know when the flag is going to be printed. Ah, interesting. Okay, after doing this, I'm not receiving anything. That could be a problem. See, until maybe what is going to happen? First, I enter 2 and I'm receiving until buffer. Listen, received nothing. Nice. Do you think the spaces are messing up? Maybe. Oh, wait, it's not working. Okay. Let me GPT my code and ask if it is correct. So the goal here is like, I don't know if it'll spawn the exploit or not, but we are rewriting it to check win function and get the flag. That's all. That's a goal here. Mm, Where I messed up, honestly, it should work. No, the function address is correct. Okay, so let's go back to the drawing board I did and what I could have done and what I've done. Like just going through everything. Perfect. So again, this time we have pointers. Again, a heap is allocated, which has input, and we have X here. So if we go back to the code again, so even again, not this. Yeah, even again, the input data is reading the content without any bound checks. So there is a good chance that we can rewrite the X. But this time we are not simply rewriting the X. We are rewrite X is a pointer here. So pointer I mentioned, it holds the address of a variable or a function or anything. It could be anything. So this time we are uh, making sure to rewrite this X. X is going to be the address of win win function, for example. So once you execute the win function, you might get a flag. I mean, this unlocks a lot of potential things. Like you can also use some kind of a shell code, right? You can also use a shell code and get a reverse shell. So that's a one way. But at the moment, this challenge is based on rewriting the X with address of win. So what happens here in the code was, so initially X is a character type pointer. Okay, and here it is being typecasted to integer type, and then it is being loaded first. So the whole point of this thing here is like the X is being called. Okay, so the call in the sense like it is trying to execute something. What it is trying to execute, whatever there in the X location. So the X, since it has BICO, which is not an address, so that's the reason whenever you try to print the flag, it is just going to tell you that okay, a segmentation fault or something. That is not your greatness. That's just how the function works. This should be X should be an address, but it is a string, so this typecasting is messing up and giving a segmentation fault. So our goal is like we need to rewrite this X to the win function so that whenever the check win function is called, which is nothing but when you want to print the flag, the win function is going to be loaded and the flag is going to be print. So yeah, this is being converted to int and the X is being executed. So since X has BICO there is no point. This is not an address, so it will give you an error. Okay, so yeah. So if you rewrite X with address of win function, you'll get flag. Very simple. So that's what is underlying the concept of this, but I don't know why it's not working, but at least the concept is clear for the time being and all. Let's should I restart the instance once? Let's see. Restarting the instance. Sometimes that could be one issue. The port will be changed. Control V, Control S. No, not receiving anything. So for some weird reason, I don't know why. Can I print this? Yep. Just printing content. So the function should be working, but I don't know, anything could happen. So the weaponization is a different story. That's I mean, sometimes you have to think too much to get it. So we can move to the heap 3 part. Use after free. So wow, this is actually cool. But let me take some break. I want to know why this is not working in the first place. I'll be back. Cool, cool. Mm, I think I should learn more about this execution flow and all. I didn't understand that properly. Mm, 1 minute. You literally said it's just an explanation on the thing. Not the compile time usually. True. However, in order to carry out this attack effectively, you will need to understand most of the heap. Things get a little complicated than overwriting is table written address of a stack. The purpose of this module is to explain some important students. What to say is that on Linux, all the source code for the standard like malloc, libc. I mean, we used libc. I used libc in the past. This one, including the code for malloc. It means the different libc's malloc operate in different ways. Libc versions and behaviors in the heap. You'll see this come up a lot when you're on heap challenge. Make sure you're on the right libc file. You might need to use LD preload to do this. Okay, or VM map should be good too. Malloc chunk. When we malloc, it returns pointer to a chunk. Let's take a look at the memory allocation of the chunk of this code. So there is a pointer. A pointer is having a malloc size of 10 hex, which is maybe like 16 or something. String copy, you're copying panda to pointer. Okay, there is a memory in the heap. This could be a panda, for example. So we see that there is a heap chunk. Every heap chunk has something called as a heap header. That is a metadata on it. And by, I mean, 16. Okay, 16 bytes. And on x86, the 8 bytes, I mean, 8 bytes is 8 bytes, contains two separate values, the previous chunk and the chunk size. The previous chunk size, if it is set, which it isn't in this case, designates the size of the previous chunk in the heap. So in this case is 21, which offers from the size we requested. Okay, the size we requested is only 16, right? So because the size we pass to malloc, it's just the minimum amount of space we want to able to run the store data because of the heap header 10 bits also. Some okay, the metadata and all add up, and so that the size is other dimensions, it will round off number up so it can deal with better things like pinning. For instance, if you hand a malloc a size of 0x7f, it will return a size of 91. It will round up 7f to 80 so it can deal with it later. And there's an extra 10 bytes of the heap and 1 byte on the both sides. Oh, what happened? Wait, something wrong. Okay, makes sense. 7f. Okay, so it's like it keeps adding this header data every time. So it gives, so whenever you ask 10 bytes, you're not only taking 10 bytes, you're also, the system is allocating you some header space and all those things. It will be more than that. Makes sense. So front and back there is some padding. What is this called? One. All of the one from the both 091 021. Also, the first three bits of the malloc size are flags which specify different things. If the bit is set, it means that whatever the flag specifies is true. Okay, winning. So when malloc frees a chunk, it will typically insert it into one of the bins list, assuming it can do something like consolidate it with the top chunk. Then the later allocation, it will check the bins to see if there are any free chunks so that it could allocate this. Okay, it's keeping track of all the removes chunks that are removed. Okay, the purpose of this is it can reuse the previous free chunks for the performance improvements. Makes sense. The fast bins consist of 7 linked lists, which typically refer by their IDX on 64-bit machines. The range is from 20 to 80 each IDX, which is an index to the fast bins. Mm, what was it called? Previous and looks like a link. Okay, that's what I'm referring to. Fast bins. Sorry. Just a minute. I had to reply to this mail. Cool. So let's go ahead and see. Right, free chunk UF explains double free buckets. It can be used to edit free chunks and help keep metadata. This can be responsible. Okay. I have pointers and we have data. We're copying them to the pointers. We're freeing them, and then we freed. Okay, we freed the pointer zero twice. Okay, that's the issue here. So is that what's the issue? How should we exploit this? So it's like just detection. I don't know. This just looks like a code for me for some reason. Hmm. Oh, so previously, since the size was only 5 bytes or something like that, but we're including a lot of more than 5 bytes. I think that could be reason because we are also rewriting some the next blocks or the next chunks metadata. So that could be one reason. I think that could be the only reason.